Together with my group mates, Arboleda, Dela Torre, and Lagaña, we're going to solve a distillation problem using the Ponchon Savarit method. The problem goes this way. So this is our problem. A 1000 kg per hour mixture containing 42 mole percent heptane and 58 mole percent ethyl benzene is to be fractionated to a distillate containing 97 mole percent heptane and a residue containing 99 mole percent ethyl benzene using a total condenser and feed at the saturated liquid condition. The enthalpy concentration data for the heptane ethyl benzene at 1 atmospheric pressure are as follows. The X-heptane are 0, 0, 0.08, 0.18, 0.25, 0.41, 0.65, 0.79, and so on. And the Y-heptane is 0, 0, 0.28, 0.43, 0.51, 0.73, and so on. And the enthalpy of saturated liquid in kilojoule per kmol times 10 raised to 3, which are 24.3, 24.1, 23.2, 22.8, 22.05, 21.75, 21.7, 21.6, and 21.4. And the enthalpy in saturated vapor in kilojoule per kmol times 10 raised to 3, 61.2, 59.6, 58.5, 51, 58.1, 56.5, 55.2, 54.4, 53.8, and 53.3. We are then required to calculate the following. First, the minimum reflux ratio. Second, the minimum number of stages at total reflux. And lastly, the number of stages at reflux ratio of 2.5.
To solve this problem, first we need to let A is equals to heptane and let B is equals to ethyl benzene. Then we need to draw a diagram of a distillation column with a feed of 1000 kg per hour that contains 0.42 mole fraction of heptane and 0.58 mole fraction of ethyl benzene. For the distillate, it contains 0.97 mole fraction of heptane and 0.03 mole fraction of ethyl benzene. For the bottom stream, we have 0.01 mole fraction of heptane and the rest is the ethyl benzene. For D and the W, we will later on find the values. Next, we need to find the average molecular weight of the two components so that we can convert the feed, which is kilogram per hour, to kmol per hour. The formula of average molecular weight is equals to the summation of molecular weight multiplied by its mole fraction. The molecular weight of heptane is 1000 kg per kmol and the molecular weight for ethyl benzene is 106 kg per kmol. So the average molecular weight is equals to 100 times 0.42 plus 106 times 0.58 is equals to 103.48 kg per kmol. Now that we have the average molecular weight, we can convert the 1000 kg per hour feed to kmol per hour, and that is equal to 9.664 kmol per hour. Then we will perform the overall mass balance, which is in is equal to out. We have F is equals to D plus W. Since F is equals to 9.664 kmol per hour, the equation will be 9.664 is equals to D plus W. Then we will manipulate the equation so that D will be equal to 9.664 kmol per hour minus W. And we can label this as our equation 1. Next, we will perform a heptane balance, and that is XFA is equals to DXDA plus WXWA. Then we will input values and it will become 9.9664 times 0.042 equals to D times 0.97 plus W times 0.01, and this will be our equation 2. Then we will substitute the equation 1 to equation 2 it will give an equation of as W is equals to 5.337 kmol per hour and D is equals to 4.127 kmol per hour.
To solve for the minimum reflux ratio, we need to use the graph minimum reflux is equals to delta E min to HV multiplied by HB to HL. By plotting and connecting the given X, Y, and X enthalpy in the graph, we can now determine the operating line. Create a vertical line upward the X enthalpy graph with the given XD is equals to 0.87 and downward with the given XW which is 0.01. The connected plotted dots in the saturated vapor, the line that intersects the 0.97 vertical line, the Y value or the enthalpy is the HV which is equals to 53.3 times 10 raised to 3 and same goes to HL but in the saturated liquid line which is equals to 21.3 times 10 raised to 3. So since it is said that the feed is in the saturated liquid, we will create a point given that the mole fraction 0.42 in the saturated liquid line and then create a line downward till it reaches the XY diagram and then create a horizontal line till it reaches the 45 degrees line in the XY diagram and a vertical line upward to the saturated vapor in the line. The created point and then create an operating line from the saturated liquid point on the saturated vapor point. From there, we need to extend the operating line till it intersects the XD or the 0.97, but it exceeds the initial graph, so we need to calibrate it and create a point. From there, we can identify our delta E min or E minimum X which is equals to also to XD which is also equals to 0.97 and our Y of H which is equals to 99.8 times 10 raised to 3. Same goes with S minimum but downwards. And now we can solve for the minimum reflux which is by multiplying 99.8 times 10 raised to 3 minus 53.2 times 10 raised to 3 dividing it by 53 times 10 raised to 3 minus 21.3 times 10 raised to 3 which is equals to 1.461. So using the XY graph, we can identify the minimum number of stages from XD, which is 0.97, create a stair inside the equilibrium until it reaches the XW, which is 0.01.
Given the reflux ratio, we can now solve for delta E by using the equation reflux ratio is equal to delta E minus HV over HV minus HL. So our HV and HL values are the same mentioned previously. So in solving, we can now get enthalpy as 133.65 times 10 raised to 3 kilojoules per kilomole. So using that as Y and XD as 0.97, we can now plot it and create a line and extend it downward that it intersects the feed point which is 0.42 and extend it again till it reaches the XW or our bottom fraction which is 0.01. So that will be our delta S. So we will now begin to identify the number of stages. So create a point based on a saturated vapor line that intersects the 0.97 and create a vertical line downward till it reaches the 45-degree line. Create a horizontal line until the equilibrium line, and then a vertical line to the saturated liquid line, and create a point. So that will be our HL. So create a tie line from the 2 points we created. From the saturated liquid point, or HL, create a line and extend it to the point delta E. The line that intersects the vapor will be our next HV point. Repeat the process till it passes through the feed point. Once it passes through the feed point, we will now use delta S for stripping. Create an operating line from delta S till it reaches the last HL point and extend it to HV. Create an operating line from delta S, intersect it with the last HL point, and extend it to the HV and create the point. From HV point, we create a vertical line to the 45-degree line and horizontal line to the equilibrium and back to the HL line. Create a tie line from the HL point to the HV point by connecting it. Create an operating line again from delta S, intersect it with the HL point and extend it to HV and create a point. From HV point, create a vertical line to the 45-degree line and horizontal line to the equilibrium and back to the HL line. Create a tie line from the HL point to the HV point. Repeat the process until it reaches XW, which is equal to 0.01. The number of the tie line will be the number of stages. So in this problem, using the Ponchon Savarit method, by counting the tie line, the distillation column has 11 stages.